validation and start, I'd like to kind of define them. I think there's a lot of different people use these words differently, but for the purposes of this presentation, this is how I'm going to define them. Verification is the process of verifying or checking that the equations are being solved correctly, so that basically it's checking that the code is doing what it was designed to do, that there's no bugs in the code. Validation for this talk is, do the equations represent a physical system? So if you program the shallow water equations, validation is checking that the shallow water equations are appropriate for the problem that you're studying. But for the purposes of like districts and applications, validation is more, you do your calibration, and validation is, does the model setup and the parameterization that you did for the calibration represent the physical system for other data sets, right? And validation is also, does the software meet the needs of the user? That's another way of looking at it. Does it have all the features and capabilities that you need for a project? You can validate a model for a field application, and if you don't have a specific feature, let's say like levee breaching, you won't be able to model that application properly. So by doing that study, you're validating that the capabilities that your modeling system has are sufficient to represent that physical system. So calibration is not something that I'm going to talk about during this talk, and I'm not going to talk about, the way you do validation for a study, but this is more validation the way we use validation for the model. Yeah. RAS has done a couple of technical reports and publications on, well, we have one VNV document that's been published, and we have different categories for verification. We split it up into different categories: 1D steady flow, 1D and 2D unsteady flow, 1 and 2D non-Newtonian flow, and also 1 and 2D sediment transport. The different types of test cases that we've done are analytical and textbook data sets, laboratory experiments, and also field data sets. These are the two documents I was talking about. One is verification and validation, and the other one is benchmarking. Gary has a talk on the benchmarking data sets right after this one, so I won't steal his thunder. I have a lot of, the RAS team has done a lot of VNV. We've done a lot of tests, both 1D and 2D. So I'm going to show a small subset because of time, and I'll go over them quickly. I'll start off with 1D. This is a verification data set for 1D steady flow. It's an analytical solution that's in Chow's book. It's a simple trapezoidal cross-section, and there's an analytical solution for backwater. And this is the results for that data set. The water surface profile matches pretty well with the analytical solution from Chow's book. That was a simple data set. This is a really complicated, this is the other extreme for 1D. I think if the RAS team did this now, you'd probably do this in 2D. It's kind of pushing the limits of 1D. But at the same time, it's such a big data set that doing it all in 2D would be difficult. I think you'd still need to do some of it, or a lot of it, in 1D. Anyway, it's 146 miles of the Columbia River, and the purpose was to evaluate flood risk for the 500-year event. The peak flows were about 400,000 CFS. And this is the model setup. As you can see, it's a pretty big modeling domain. It had a stage boundary condition and the downstream end at the ocean boundary. There were 208 lateral structures, 106 storage areas, It was calibrated to 3 events and then validated for 2 different events. And this goes to what I was talking about when, defining what validation is. When you're doing a project, this is how you validate. You calibrate with some data and you validate with other data. You can also do something that's called cross-validation. Usually we don't have enough data for this, but cross-validation is like resampling your whole data and testing with parts of it. Like, I don't know if you've heard like jackknife techniques and things like that. It's used a lot for like machine learning as well. But anyway, for applications, validation it works like this. When we're doing validation, sometimes we'll have only one set of, one experiment, and we kind of calibrate to that. But we also call that validation because we are demonstrating that the equations represent the physical system. We're validating that aspect. Okay, but some people might say, "Oh no, that's not really validation. That you just calibrated the model." Well, that's true, but we also validated that the model can represent the physical system. Okay, anyway, so this is the mouth of Columbia River, and this is the results for one of the flood events, 1996 event, and it represented pretty well the peak water levels. Now, moving on to 2D data sets, this is a kind of a classical data set that's run a lot by shallow water equation models. The purpose was to verify the temporal schemes, time-step convergence, look at numerical dissipation, and it's just a rectangular flat basin, and you initialize the water level with a cosine wave, and then you let it go. And because there's no friction in that basin, in that bathtub, the water sloshes back and forth. And if there's no numerical dissipation, it should slosh forever. And on the right, it's like all the equations. And if you see any decay in the wave amplitude, then that's numerical dissipation. And so this is, we use this one to test like how the implicit weighting factor that we talked about this week, how that improves the solution, and how reducing the time step improves the solution. And the plot on the left shows the water surface sloshing, back and forth from one side to the other. And then the time series on the right are the time series at just one end of the basin. And you can see how the time step and the implicit weighting factor change or affect the solution and the dissipation. The theta factor has a big impact when the time step is very big, but if your time step is very small, then it has a smaller impact. And that's what you see in those results. That's the takeaway. Okay, this is another data set that we ran, a steady open channel flow. There's an analytical solution that was developed by McDonald in his PhD dissertation. And it's for the shallow water equations. It's a variable bed slope, just below supercritical flow. So the Froude number was up to 0.986. And we use this to look at grid convergence. So basically you run different resolutions and you see how the model error reduces with grid resolution. And then you can use that to compute the order of the overall accuracy of the model. So in this case, the order was approximately 1. And that's because even though some terms are second order, like the pressure gradient term, there's other terms that are only first order, like advection. And so the overall accuracy of the model is first order. And that's this plot that's on the lower right-hand side. This is a very interesting data set for wind. Wind is a new feature in 6.0. So it's an analytical solution for a circular basin with a flat bottom, and it has a variable wind over it. The vectors on the upper right plot show the wind, and the mesh is a polygonal mesh, mostly hexagons. And there's an analytical solution for that. This one has Coriolis in it. There's one without Coriolis. And so the water just goes around, and this is the water surface elevations computed and analytical for that data set. I mean, we have profile plots and time series and things, but these are pretty interesting to look at. So you can see that because the wind is on the northern side of the basin is going from left to right, the water kind of piles up on the corner, and on the lower side it's kind of does the opposite. It's symmetrical. This is another very interesting data set. I like it because of how they derive the analytical solution. It's a kind of a manufactured solution. You take your equations and you say, I want my solution to look like this. And what they said is, I want my velocity to be constant. And so they plugged that into the shallow water equation, the momentum equation, and then integrated that and came up with the water surface profile. And it's just super clever, you know? And because the velocity is constant, then your advection terms drop out, and the solution is valid for both diffusion wave and the shallow water equations, which is also really cool. And this is the analytical solution for the diffusion wave equation for this data set. So what you're looking at here is the flood wave is going from left to right, and the different profiles are different snapshots. And the analytical one is the one with the lines with markers, and the computed ones are without markers. And the model did a pretty good job of reproducing the analytical result. And then this is a velocity profiles compared as well. The velocity should be either 0 or 1. So any deviations from that are caused by numerical errors. But it did a pretty good job, the model as well, in reproducing the velocities. The velocities are much more difficult to get correctly than the water surface elevations. This is another commonly used analytical data set. It's a dam break problem. Two cases: one where a wet case, so there's water on both sides, but on one side it's much higher elevation. So in this case, the water on the left, the initial water profile was 10 meters high, and on the right it was 5 meters, so pretty large difference. And then you let it go. It's an instantaneous dam break. And so the lower left plot shows the analytical water surface and velocity profiles at 10 and 20 and 30 seconds. And on the right is the case where the right-hand side is dry. It also shows the water surface and velocity profiles. The wet and wet case, the results are shown for both the Eulerian-Lagrangian model and the Eulerian model for both cases. The Eulerian-Lagrangian model does a pretty good job for the wet case, except for these deviations here. There's some errors here. But for the wet and dry case, instead of producing a rarefaction wave, this kind of like sloshing wave, it produces shock wave, this steep wave here. And this was one of the data sets that when we were doing our VNV several years ago, we looked at this data set, found this issue with it, which was already known for Eulerian-Lagrangian models. And we said, we got to do a better job. And this was one of the data sets that kind of motivated us to develop the Eulerian solver. And as you can see, the red line is the Eulerian solver, and it does a much better job at reproducing this analytical data set. And even the wet and wet case, it just conserves momentum better, and it's more stable for this data set. Has better time-step convergence as well. Okay, one of the new features that we added for 6.0 was Precip, and so we wanted to do some validation for some data sets that had Precip. And this is a really interesting Flume data set where they had like metal sheets, 3 of them. They put them together and then they put these obstructions in the Flume to kind of give the water a longer travel time and redirect the flow. And we modeled this with both the diffusion wave and shallow water equations. And this is on the left is the velocity, the velocity results, and on the right is the time series of flows at the outlet. The purple line is the precip. So they had sprinklers on top of the flume, and they turned the sprinklers on had a constant rate, turned them off for a while, and turned them back on. And there were multiple experiments for this one. There were 3, and we ran them all. So this is a really neat Flume experiment. And it's also interesting to look at the differences between running shallow water equations and diffusion wave. For this particular data set, the shallow water equation model did a much better job than diffusion wave did. Another new thing that we added in 6.0 was we added infiltration methods. We have deficit constant, greening amp with redistribution, and curve number. I'm going to show results for greening amp because it's kind of like the most interesting one, and greening amp with redistribution is even more interesting. And this was a lab experiment where they simulated infiltration and then stop and let the soil kind of recover, redistribute, and then simulated more infiltration. And so the plot on the left, you can see the computed infiltration rates after during 2 rainfall events with a period of no rain in between. And in general, the model did a pretty good job of representing simulating this lab experiment. The table on the right shows all the green amp parameters, like the saturated water content and the pore distribution index. Yeah, so this is available in 6.0, the green amp with redistribution. This is a Flume experiment. I talked about this, already showed this earlier in the week when we talked about turbulence. But it's that sudden expansion Flume experiment that has a recirculation zone, and it's really useful to look at a turbulence and the turbulence coefficients. This shows a comparison of the non-conservative turbulence formulation and the conservative one. The main takeaway is that the conservative formulation does a better job of reproducing the velocity profiles, and specifically the return flow. And when you have this recirculation zone, that there's a return flow here, and the conservative form does a better job of capturing that return flow. It produces a stronger return flow. And this is I think pretty large Flume experiment, a flow through a bridge, and this was done by Professor David Parr and other folks outside of HEC. It wasn't done by HEC, but it's a really neat, really detailed resolution model of flow through a bridge. And this is the kind of Flume experiment setup that they had. And this is the terrain. They started off with just the kind of the bed, and then added the piers to the bridge and to the terrain. A super small cell size, 0.1 foot cell size, kind of away from the bridge, and then near the bridge, near the piers, 0.01 foot cell size, so extremely high resolution. And this is the model setup. There was a flow boundary condition upstream, stage downstream. This is a zoom in of the mesh near the bridge, and so they set up break lines to capture the terrain, and also the piers are represented in the mesh. And this was run with about 20,000 cells and the shallow water equations. This shows the water surface profiles for various runs that were done for that Flume experiment. And in general, the model did a pretty good job of representing the flow and the water surface elevation through the bridge, the energy losses. All the other models were also run for this data set. SRH was run, and RAS compared pretty well to the other models as well. This is a more complicated field data set, the New Magic Floodway and levee breaches. I was actually in Mississippi during this flood, and I remember all the flooding that happened and going to the river to look at how high it was, and it was kind of a big deal at the time. So during May of 2011, the Corps activated or blew up portion of the levee to activate this floodway to alleviate the flooding. And before they did that, the USGS went out and put out 38 pressure transducers to measure the water levels during the event after they breached the levee. And then after, I think, a few days or after they did another breach at the lower end to kind of let the water out of the floodway, let the water drain out. So the floodway is about 40 miles long and 10 miles wide, and a resolution of about 500 feet was used for the simulation. And the table shows kind of the model setup. I won't go into all the details of that, but it was set up with variable roughness based on land cover. And this shows the maximum water level, a comparison of the maximum water levels at the different USGS gauges. And in general, the model did a pretty good job of representing the maximum water levels at all the stations. There wasn't any that were particularly off. This is a summary of the results here. The max difference was 0.68 foot. The mean differences was about 1/3 of a foot. These are some representative time series, near the upper end and near the middle and at the lower end of the floodway. And again, the model did a pretty good job of capturing the timing of the event and also the amplitude of the event. This is a little or very different. I know we haven't covered non-Newtonian modeling in this class, but I thought it'd be really cool to show this. This is a dam that failed in Brazil. I want to say February 2019. Stan can correct me if I'm wrong, but I have an animation here. Let me show you the dam. This is really, really impressive. Yeah, so the dam, it was a mine tailings dam, and it killed about 270 people at least. And there were people working at the time nearby. You can see people there. There's a train going by, and it's obviously a debris flow, right? Super high density flow, non-Newtonian. It almost looks like lava. And this is the HEC-RAS result. The red line and the polygon represents the flood extents of the debris flow. And I'm going to show an animation comparing RAS results. So as you can see, the model did a pretty good job of representing the flood extents. The timing was also pretty good. There were several locations where people had the arrival times of the debris flow, and they were pretty accurate as well. It was it was January. That was my fault. The Mudflow, the maximum height was 10 meters, which is pretty amazing. There's 12.7 cubic yards released in 300 seconds. So pretty crazy event. It was modeled as a Bingham fluid within RAS with a yield stress of 800 pascals and viscosity of 100 pascals per second. So if you're not familiar with those numbers, those are pretty big numbers. It was a pretty viscous event and with the high yield stress. And on the right, there's a bunch of comparisons of Mike 21 results with HEC-RAS. Mike 21 also has the ability to model debris flows as a Bingham fluid. And so the comparison was done with the same exact parameters. And the model results were compared, and they compare fairly well. I will say RAS, the equations are slightly different because we have slope corrections and Mike 21 does not. So it's not, a perfect one-to-one comparison, but pretty close.